This video is over Unit 6, Lesson 2, and it's over writing inequalities based on real life situations. So I'm going to zoom in a little bit on this problem so we can see it just a little bit better. So on a farm, each duck eats 6 pounds of food per week, and each chicken eats 4 pounds of food per week. If you can afford 500 pounds of food this week, write an inequality representing all the possible combination of ducks and chickens that you could own. Okay, so let's let ducks be X, and let's let chickens be Y. And so we want to write an expression that models the total amount of food being eaten by the ducks and the chickens. So it's going to be the amount of food for the ducks and the amount of food for the chickens. So 6 pounds times how many ducks plus 4 pounds times how many chickens. And we can only afford 500 pounds, so we have to feed less than or equal to 500 pounds. I wrote this in the wrong spot. You probably really should have put this right here. It says state 3 possible solutions to represent the amount of food for the ducks, or the amount of feed for the ducks and the chickens. All right, so we have a lot of different options. If you graphed this, there would be a ton of different solutions within the shaded region. If we had, for instance, 10 chickens and 10 ducks, we would only be using 100 pounds of food. We'd be using 60 for the ducks and 40 for the chickens. 100's less than 500, so that's a solution. We could also have, let's say, 20 ducks. That's 120 pounds of food. And 25 chickens. That's 100 pounds of food. So that's still only 220 pounds of food. Now, most farmers aren't going to buy 500 pounds of food if they're only using 220. So what we want is we want to figure out how to maximize this food. So I am going to try to find a solution that would be on the line. And so let's see here. I'm going to start with 50 ducks. So 50 ducks would be 300 pounds of food. That leaves 200 pounds of food for the chickens. 200 divided by 4 is 50. So I could have 50 ducks and 50 chickens, and I'm going to use all 500 pounds of food. And there's lots of different solutions that would work to use all 500 pounds of the food as well. So lots of different solutions for that one. All right, so let's take a look at B. It costs $5 to buy a pen and $3 to buy a ruler. If you have $50 to spend, write an inequality representing all the possible combinations of pens and rulers you could buy. So I'm going to let pens be X and rulers be Y. Once again, it's $5 times the number of pens plus $3 times the number of rulers, and I only have $50. So if I bought 5 pens, I still have $25. And so I could buy 8 rulers and then still have $1 left. I could buy 0 pens and 16 rulers and use $48. I could buy 10 pens and use all $50 and then not buy any rulers. I could buy 1 of each. There's lots of different solutions that work for that. A shipping company needs to deliver some clay pots. It will be paid $1 for each safely delivered pot and fined $5 for each broken pot. If the company wants to earn at least $2,000 for this delivery, write an inequality representing all of the possible solutions, combinations of safely delivered ceramics and broken ceramics. Then graph it. Okay, so we're going to let safely delivered be X, broken be Y. I get $1 times how many ever safely delivered, but I'm losing, so I'm subtracting $5 per broken, and I want to make at least $2,000. Remember, at least is greater than or equal to. Okay, so typically when you're graphing these, we talked about this in class, you want to find, the easiest way to graph them would be to find your x and y intercepts. If you solve this for y, you would end up with this. And if you start at negative 400 and go up 1 over 5, that's going to take you a long time to get any information that's really helpful here. We are only concerned with solutions in the first quadrant, meaning like if this is your xy axis, we have first quadrant, second, third, and fourth. And we're only concerned with this quadrant because then both x and y are both positive. We can't have a negative amount of deliveries, so we only care about the positives. All right, I'm going to erase that so I have that room back. So we are going to start by finding our x and y intercepts. Our y-intercept we get by letting x be 0. And so we would have this. This 1 times 0 is basically gone. It's just 0. So we divide both sides by negative 5. Y equals negative 400. We're going to do the same thing for our x-intercept, but we're going to let y be 0. And I'm going to have to move this stuff out of the way here in a minute. But so this is gone. 2,000 divided by 1 is just 2,000, so my x-intercept is 2,000. So I'm going to erase this work so that I have this information, but I also have my space. Okay, so my y-intercept was negative 400, and my x-intercept was 2,000. I am going to let my axes on this actually be labeled by 500s, and so every other one I'm going to label with a 1,000. And if you were in class and you were watching this, remember we actually looked at Desmos and graphed this on Desmos to see what it would look like to get a better feel for what kind of graph we should use. So I'm labeling every other one of these by 1,000. I'm going to do the same thing on my y-axis. I think that should be good. Okay, so my x-intercept is 2,000. Now my slope, we can see right here, is 1 over 5. That means I could go up 1 over 5, or I could go up 1,000 over 5,000. So that's what I'm going to do. I'm going to go up 1,000 and over 5,000. And the reason I can do that is because 1,000 over 5,000 simplifies to 1/5. I'm going to do that again. Oh, I didn't quite go over far enough, did I? Let's fix that. So up 1,000 over 5,000. So I should have a point right here. Up 1,000 over 5,000 is going to go slightly off my graph. Connect those points, and it's less than or equal to, so I'm going to shade in there. And so any of those points in that solution is going to give us our possible combinations. And so we have 2,000 safely delivered, 0 broken. We have 8,000 safely delivered, and we could even have like 500 broken if we have 8,000 safely delivered. We could do 11,000 and 1,000. Lots of possible solutions once you get that graphed. Okay, so now let's look at another one of these. We're going to be graphing this one as well. So we have it costs $1 to buy an apple and $2 to buy a mango. If you have $10 to spend, write an inequality representing all the possible combinations of apples and mangoes you could buy. So let's let apples be X, mangoes be Y. We're going to spend $1 times how many of our apples we buy, plus $2 times how many of our mangoes we buy, and we only have $10. So we have to spend less than or equal to $10. So you could solve for y here. Once again, we're only interested in this first quadrant because we have x and y that have to be positive. Instead of solving for y, I'm just going to go ahead and find my x-intercepts, or my x and y intercepts. So my x-intercept, I let y be 0. That's going to equal 10. My y-intercept, I let x equal 0. That's going to be 5. I'm just going to go each one of these by 1. And you always want to label. Don't assume that people know what your axes are or what your tick marks are representing. You don't have to label all the way up like I'm doing. You can just label a couple so that we know. I just like to have them so I don't have to count. So my x-intercept is 10. My y-intercept is 5. I could solve this for y, subtracting that 1x on both sides, and then dividing by 2. It's going to give me negative 1/2 x plus 5. And so I know that my slope is negative 1/2, and then that can just give me some more points in between that x and y-intercept. Lots of different options there to graph. Connect those. It's less than or equal to, so I'm going to shade below. And then it says determine 3 possible combinations of apples and mangoes. Well, here's one. 1, 2. That's within our range. 5, 2. Could buy 8 and 1. Could buy 6 and 1. Lots of combinations of apples and mangoes. All right, last question. So this is really similar. We have $2 per orange and $3 per coconut. We have $20 to spend. We're going to let oranges be X, coconuts be Y, very similar to D. We have 2 times the number of oranges plus 3 times the number of coconuts. It has to be less than or equal to 20. And so if I solve for Y, which you can do and check yourself here, you should get this. And 20/3 is 6.7 roughly. So you can write it as 6.7. I just really don't like to have to round decimals. But that is going to be where our y-intercept happens, is a little before 7. So I'm going to go ahead and put a point there. And then I'm going to go ahead and find my x-intercept based on this original equation. So 20 divided by 2 is 10. Put that here. Connect those. Has to be less than or equal to. It says if you buy 4 oranges, how many coconuts can you afford to buy? Well, 4 oranges would cost $8, which means I have $12 left, which means that I could buy 4 coconuts.